Hi, so you can see this picture, right?
Yes, I can see a picture. And I'm trying to understand what's going on. Hoping I'll understand it. Go ahead. Yeah.
Well, I don't know. So that gray region is a usual depiction of the moduli space of elliptic curves. I hope you agree. I mean, you know, or
well,
some edges identified and so on.
I mean, part of the problem is that I've just haven't thought about this in such a long time, or I'm really hoping that I didn't have something screwed up or not too bad.
Well, I seem to find so anyway. Okay, you can.
Well, can I ask an interrogation? Can I take an interrogation point of view?
No. Come on. Let me say what this is. So I was thinking that you were saying that gray region not only is the moduli space of elliptic curves, but at least is awfully close to some moduli space of acute triangles. And I agree with you that. So I drew how I thought it was supposed to go. Maybe I'm wrong. Maybe this just screwed up. Maybe I shouldn't have put the vertices here, but I put the vertices here, two of the vertices at -1 and 1, because then if the third vertex was right on the circle, this big circle here, you'd get a right triangle, and that sounded like something you said, and that sounds good. So it's sort of like on the edge of not being acute. But then the thing that's bugging me is what's going on these vertical lines, because I thought you had said that when this vertex here hits one of these vertical lines, the triangle becomes isosceles.
Some triangle does become isosceles, yeah.
Yeah, and I don't think this triangle becomes isosceles, because I just tried to work out what the lengths were, and it just didn't seem like it was working.
Yeah, it could be that there's a mystical factor of 1/2. You know how people have these factors? I say displacement. Well, I very much want to ask questions about.
Okay, now you can ask questions. Now that I've said what I'm worrying about.
Okay, so this we can think of this as a picture, roughly speaking, picture of the upper half plane.
Yeah.
So yeah, upper half plane is a kind of parameter space or moduli space or something like that. Well, or something. And yeah, so I would like to have a name for this parameter, and maybe you call it tau or something. Yeah, there's probably conflicting conventions. I just want you to.
Everyone calls it tau. Everyone calls it tau. Yeah.
I'll bet there's some people who.
I'm sure you can dig up some.
Okay, so tau. Okay, so we're calling this number tau. Okay, and you've got some values of tau marked on this sort of real axis, and which is sort of a ideal boundary points, and the imaginary axis, which is right in the middle of the parameter space.
Mm-hmm.
Well, except that you wrote them as like y. Yeah, you just wrote them as y values on the y axis.
Yep.
But we could have written them as the complex numbers. Tau is a complex number here.
Yeah, I just stole this picture from somewhere. So.
Okay, so, and I'm imagining that one of the important interpretations of this picture is that tau is supposed to generate a lattice. Well, tau together with one other special generator, which I'm imagining will be 1.
Yeah, the usual, that's the story that causes people to draw this picture, except for the red triangle. Yeah, that's the usual story, yeah.
Okay, so
the Gaussian elliptic curve is here at 1.
Say that again. The Gaussian.
The Gaussian elliptic curve is here at 1, or I. I mean, it's just pointing at 1.
That's right, at I. That's right, at I.
And then the Eisenstein is right here, or equivalently right here. That's a 60-degree angle.
Okay, let me think about what you're saying. Let me think about what you're saying. 1 and 1. That's a Gaussian, right? That certainly looks like a Gaussian thing there. Okay, I agree with that. Let me think. 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 Let's see. Let's see. Okay, that's the Gaussian right there, and that's the Eisensteinian right there. Well, just any chance you can act as my mental cursor here when I say that's the Gaussian right there, you can point to the Gaussian, and then when I say that's the Eisensteinian right there, I mean you already did it, but okay, so that's the Eisensteinian right there.
Yeah, and also
Gaussian is
there.
yeah, right, that's right. Okay, so let me think. So let me think. So
Yeah, so I've just been getting ready to tell everybody, oh, all the points in this gray region correspond to acute triangles, and they do give some acute triangles. And I was going to say the ones on here, this arc, give right triangles, and that's true. We talked about that famous old theorem, Greek theorem. And then I was going to say, oh, and the ones along here give isosceles triangles. And then I just like worked out the distance.
yeah, yeah. Well, I mean, I mean, they give isosceles triangles. That's right. Okay, maybe you. I think. Boy, this is confusing. Let's see. I keep on thinking you've left out some semicircle here, but let's see. After that. Yeah, okay, wait. There's something bugging me here. There's something bugging me here. I think you did leave out the important semicircles. You've got semicircles of radius 1. Shouldn't there be semicircles of radius 1/2 in the picture? Am I confused? What am I trying to say here? Unless this is some convention that I'm just not familiar with, but that would seem strange.
You're worrying about ones that should be like this?
Well, so there are like some sort of hyperbolic triangles that, so like, what do you think of the, right? There's some sort of hyperbolic triangles that are supposed to be the fundamental domain with respect to something like, I don't know, SL2R or SL2Z or GL2Z or something. So can you, so you think this great thing is probably a fundamental domain with respect to SL2Z?
Yeah, I think that's what it's supposed to be. Yep. So like adding 1 to your generator tau doesn't change the lattice. So these two are at the right distance from each other. And conformal inversion maps this gray region to this this thing here. I think some about this looks like some version of conformal inversion is supposed to map this gray region to some other bunch of, I guess tau goes to -1 over tau is some transformation that gives you the same elliptic curve. I don't take responsibility for these small circles down here, or at least, that is, I would have been happy to find a picture that just didn't have those.
Well, I mean, maybe I should really go home and think about this before we try to.
Yeah, that's fine.
Really
Yeah, I don't
clarify.
want to ruin the whole.
But let me give my, my answer is, my rough answer is that there's a semicircle that I was expecting to be drawn here, a semicircle that would, let's see. So
I can think of a semicircle that would be fun to draw here, but I don't know if it's the one you.
what's the one you're thinking of? I mean, I'm thinking of the base would be from 0 to 1. Yeah, the semicircle with
Well,
base.
there is a semicircle with the base. Okay. Yeah, well, there could be that, but I don't see how that's going to help.
Well, that will
I'm
make.
happy to stick it in there.
Well, so use that as the base. Let me. You sure that's not supposed to be there? Oh boy, am I confused.
Maybe it is supposed to be there. Like I said, I didn't draw this thing. I don't know why they drew it. I don't know what these things are supposed to be. I don't know what that distance there is supposed to be. It's sort of weird. But that seems weird to me actually, but I didn't think any of that mattered because I thought all the action was happening up in this strip here. This gray region.
Okay, let me think. I think. Yeah, I think, okay. No, I think I've got it. I think there is something that I want to add to the picture, and that is that, so this is just showing fundamental domains. I'm guessing, if I'm not too badly confused, but it's very annoying that I couldn't just instantly tell you all the answers. This is, showing us the fundamental domains with respect to SL2Z. But I think the picture actually becomes easier to understand, and you see the acute triangles better if you look at the fundamental domains with respect to GL2Z, which is, that's an index 2 thing. SL2Z is index 2 in GL2Z, if I haven't screwed up. And so that means we're bisecting each of these fundamental domains into halves.
Okay.
And so in particular, the imaginary axis is not in your picture, right? That's just an auxiliary line. That's not part of this tessellation. But it should be. I'm saying those are the bisecting lines that we should add to the picture, but not just that fundamental domain should get bisected. They also get bisected. And when they get bisected, then that semicircle I want to be appears as one of those bisecting lines. It's you see it. Can you see the things that are getting bisected by that?
Yeah.
And yeah, so I think, I may be using some slightly different fundamental domain, but it should work out. I think I'm saying that the picture becomes much more self-explanatory when you put in those extra lines. In other words, what you've got is those blue lines that you've drawn. Those are where all the right triangles are.
Which blue lines? So where's the moduli space of
the blue
yeah.
semicircle, the blue
okay, yeah,
curved
sure.
lines. That's where all these right triangles are.
Oh, so you're saying, well, okay, so I mean, I agree that there are isosceles triangles along this line here.
That's right. That's right.
Okay,
Those are yeah, that.
yeah.
No, sorry, no, actually, isosceles triangles along this one next to it, the blue line. Okay,
No,
did I say it
no,
wrong? Did I say it
no,
backwards?
that's exactly what's not, that's exactly what I was complaining about. No, I
No, I'm
mean,
pointing to a different blue line. That go
that
up.
blue
Up,
curve?
no, up, go higher. And now move to a blue line. Same, right there.
No, that's exactly where they're not. I mean,
That's where, yeah, that's the apexes of these isosceles triangles, whose base is, as I say, the magic base, which is 0 to 1.
0 to 1.
Yeah,
Oh, so
0 to
I
1.
should not have this triangle here at all. You're saying I should just draw a triangle with base 0 and 1. Is that what you're
Yes,
saying?
that's what I was trying to say. Yes.
Oh, you should have said that a long time ago. Okay.
I did sort of say it. If we went back into the tape, I think it would be there, sort of. Well, sort of.
Okay.
Uh,
Okay, so that will change everything for starters.
I mean, I certainly said to draw the semicircle with that base, but I meant that, you know, take that base as the base of the acute triangles that we're drawing. And yeah.
But then what's this? What's the role of this?
So can I say another magic thing here? So
Okay.
another magic thing, I guess you have to think like Escher, which means you just want to checkerboard color this black and white. And you can't understand the picture unless you checkerboard color black and white. And in order to do that, you have to bisect everything.
Yeah, I can do, yeah, anyway.
And you know, then the blacks will be the left-handed acutes and the whites will be the right-handed acutes. I think it'll work out. I think it'll work out. And you know, I'm really annoyed that I had to really think about it this long, but I think it'll work out. We're just using maybe a slightly different way of thinking about things, but it'll work out. You know, there'll be tau. 1 and tau will be the generators of the lattice.
So, okay, let me say what I like and what I don't like now. So
it might help too if you could bring up that checkerboard Escher picture, but go ahead. Yeah, say what you were going to say.
So I'm going to draw, I mean, with my cursor, I'm going to draw triangles where the base is going from 0 to 1.
Yes.
And the apex will be in this region here. This region that I'm indicating. Okay.
Yes.
Now, so certainly if the apex is right on this line, we'll have an isosceles triangle. Because this line is halfway between 0 and 1.
Yes.
So that I'm happy with.
Yes.
Now, are you saying, now what about the points along, what about when the apex is along this curve here? Are you saying that those are right triangles? That doesn't look like, is that? I mean, no.
Sorry. No. You're still using the wrong base. You're still using -1 to 1. You got to forget -1 to 1. When I say base,
No, I'm doing 0 to 1. I'm doing 0 to 1.
Yeah, and that means that's where the semicircle goes. That's the base of the semicircle. That's the base of the triangle and the base of the semicircle. So again, there's this semicircle that you haven't drawn, which is the boundary. It's this thing that bisects.
I shouldn't have to move everything over. I should be able to move one. If I move everything over, then I'm not doing anything, right? Sorry, which semicircle do you want me to stick in? A semicircle of?
A semicircle of radius 1/2. Yeah, centered at 0, centered at 1/2.
You seem to be shrinking everything by a factor of 2, and I shouldn't have to shrink everything by a factor of 2.
I know, I think you should, but let me. I could be all screwed up, but I feel screwed up because I feel like I'm looking at the wrong picture. I'm not looking at the Escher checkerboard.
Do you want to draw? Do you want to do it? Take us. Can you draw? You want to draw it? I can get rid of this.
We could also, couldn't you just find one online and put it up here?
Put one what up here?
A picture, a copy of the picture, I'm imagining. It's,
This is what there was basically.
I was hoping there was an Escher version.
Well, anyway, let's maybe stop you about this now.
Well, let me try. Let me try. All right. So, okay, the graph paper is visible now.
Yep.
All right. And I'll take that to be 0, and I'll take gas, I'll take that to be, sorry. I'll take that to be 1. Okay. And so I've got a semicircle here. Okay. And yeah, so the yeah, I'm taking the lattice generated by 1 and tau. And tau is, for the moment, is, it's a complex number in this thing up here. But this thing up here is, let's see. Yeah. So let's see. So where is, let's see. Okay, square root of 3/2 or something. So where's the, what is it? 1.7. What am I trying to say?
Yeah.
Or 0.8.
0.866.
Yeah. So what does that mean? That
A
means
little further up than that thing gives you an equilateral triangle. You can just draw an equilateral triangle.
I mean, is it let's see.
About right, yeah.
Is it there? What am I doing?
Yeah, that's close enough. That's
I'm not sure that is close enough. Let's see.
what we're trying to do, but that's an equilateral triangle. Well, you could have made it a little shorter, but it's not much shorter.
So I wish I could see the other picture right now.
You want to see
I
thought you were going to draw this moduli, this shaded region that matters.
Well, I mean, okay. I want to draw all the isosceles triangles. So okay, so there's all these isosceles triangles in here.
Yeah.
But then there's these other ones I'm not very good at drawing. And
Right.
where do those go? Do those go? Is it like here? Those are all isosceles triangles? Those reds?
Yep.
Okay. And yeah. So if I identify parallelograms or acute triangles with their stereoisomers, or whatever you call them, then it's 1/6 of this it's right. So I took this thing above the semicircle, the strip above the semicircle, and I, broke it up into 6 isomorphic parts with Z mod 3 symmetry. But that includes some, that's not all in SL, that's in GL2, Z.
So these are
fundamental. Yeah, these 6 things are fundamental domains for GL2, Z.
So they're giving you all the unoriented similarity classes of acute triangles.
Yeah, that seems right. Unoriented acute triangles. And again, including sort of honorary acute triangles, the right triangles on the boundary. Yeah. So if you want oriented triangles instead, which you do when you're dealing with holomorphic stuff, you just want to stick 2 of these fundamental domains together. And you could stick together 2 of them that are really inside this picture, or you could use the neighboring one, and that's apparently what you're doing, right?
I don't know what I'm doing. I mean,
I'm saying there's this neighboring one over here. And so there's this very badly drawn thing here. So you're going up there. So you're right, you have to take 2 of them. So you take this one, and that's how you're getting your fundamental domain for SL to Z.
Okay. Well, okay, so
I'm not saying I'm telling the story the best way, but I think we're at least straightening it out.
is there any way to take the region that you've currently indicated with those 2 red dots, that double region, and from a point in there to efficiently get an acute triangle? So
yes, but the trick is don't use this one, use this one.
Okay.
And the base, the magic base, is 0 to 1. And it's isosceles if it's up here. It's it's isosceles if it's on the red lines. It's right if it's on the black lines. So so maybe one of the punchlines, maybe I didn't quite say it out loud, right, is that the moduli stack, when you think of it in the right way, the moduli stack of acute triangles is basically the same as the moduli stack of elliptic curves, except the boundary conditions are a little bit different. With the moduli stack of elliptic curves, you just kind of hit a wall. When you run into a right triangle, you just kind of hit a wall. You don't go past that. There's no acute triangle past 90 degrees. But with the moduli stack of elliptic curves, you have some sort of funny Pachner move boundary conditions that when you hit a wall, well, I guess you don't bounce off the wall, well, or maybe you do in the right way. But anyway, it's like a Pachner move or something. Isn't that right? I'm hoping that's the right way to think of it. You've got a right triangle. I mean, you've got a parallelogram. What am I saying? You've got a, what am I trying to say? When the parallelogram becomes a rectangle, then you make the Pachner move from this triangle to this other triangle or something like that. And that takes you, from this point on the moduli stack over to this point on the moduli stack or something. I'm saying that in a very sloppy way. Much better way to say that. But the 2 moduli stacks are basically the same, except there's this different boundary conditions. What do they call that? Absorbing barrier? Or hitting a wall. What do you call that? I don't know. But
Reflecting.
and the other thing is some sort of periodic thing. Like I say, and I think you can think of this periodic thing for the elliptic curves as this like Pachner move on the right triangles that you're bisecting your rectangle into. I didn't think that through very carefully, but I think that's true. But also, I think as we're staring at the picture here, I think it's making much better sense. And
Yep.
and
Okay. Yep. It's weird.
and you know, and to get the acute triangle thing, you really should, you know, move the thing you were pointing out to as the very traditional one. You should move that over by 1/2. No, you should join it with the other thing, because I mean, that doesn't look like an acute triangle to me right there. But if you put it over there, then it is an acute triangle. So you know, for the acute triangle story, I think you should really not use this one over here, but instead use, you know, this one over here. Something like that.
Yep. Okay. Yeah. No, I didn't get that when you were talking
The base
about
is down here. Yeah, I was being incredibly sloppy, and I didn't understand it until you just retaught it.
Okay. That I was hoping there was some way to save this all. I just could not see how to do it. But okay.
Yeah, right. You got me really scared, but I think now the moral of the story that I'm thinking of is you know what I was saying before, that I mean, I hate visual thinking, but this is one of those things that if you're looking at the right picture, it's sort of obvious. And the right picture is the Escher picture. What I think is the Escher picture: black and white, good and evil, left-handed and right-handed things, which are missing in the picture that you showed me. You tricked me by showing the picture without the dividing line between good and evil.
No, that's not what the problem is. But anyway,
yeah,
the problem was the difference between the blue stuff that you've indicated now.
Yes.
And the traditional strip that's one over, or if you don't want to know what I mean, it consists of the next two regions. Sorry, yeah, I can't point, but you know, instead of the blue stuff, if you like go to the next red line there, that's the one that they're always talking about. So that's the one that I used, and so it's sort of cool and weird that.
Yeah, this is a better one for certain purposes. Actually, for a lot of purposes, it's actually a better one. But also, no. Another deep moral of the story is that somehow it really is better, ultimately, to think in terms of GL2Z instead of SL2Z. I mean, there's a lot of tension between that. They each have their own disadvantages, but even when you think about holomorphic stuff, there is some really good story about this GL2 common Z.
Yep. Yeah, no, you've sold me on that. I wasn't. Okay. Okay, that's good. So why don't you tell me what you were actually going to tell me? I know I put you on the spot here. I was just thought it would be fun to just like ask you.
Sure, no, that was great. That was great. That's you know, it's fun for me. Might not have been fun for anybody watching us, but for me, that was very fun.
I think it should have been fun.
Okay. So yeah, okay. Well, right, and I may plead being sort of mentally out of it right at the moment to being some version of, what is it called? Jet lag. I don't have a jet, but some version of jet lag. But I think that is causing me to have an excuse to sort of think very concretely at the moment. In other words, there's some really beautiful highbrow stuff that we really should be thinking about very soon. But apparently we're not going to do that today. Apparently we're going to try to think very lowbrow stuff today. Well, let me try to jump into lowbrow stuff and then maybe possibly sketch a little bit of the surrounding conceptual picture that makes it more highbrow. So what are we trying to do here? So Right. Well, maybe I can even refer to pictures that we actually drew last time if I can. Damn. If I can manage to find those pictures here. I'm just not good at referring back to pictures. Is this? What's going on here? Maybe this is the picture. Does this look like stuff from last time? I think this looks like stuff from last time.
Yep.
Yeah. So, right. Can you see my cursor here where I'm kind of in the middle of the page? There's that little, right? We're making this, we're wrapping this up. We're wrapping up this genus 1 Gaussian elliptic curve into a genus 0 thing. And we're making a design out of that. So it's this genus 0 design. And okay, so that was just to remind us where we are. Now I'm going back to our current page. And where is that? Okay. And so I got to draw a picture like that here somewhere. So let me, why I'm so disorganized. Let me second draw a copy of the correct picture here. So, oh boy. Okay, so what does it look like? It looks like well, A and B in red, and C and D, that's in green. Is that green? Yeah, it's green. And E and F and G and H. Is that right? That was supposed to be in blue, though. Blue. E is over there, and F and G is H. And now what am I supposed to put in here? I'm supposed to put in the boundaries of the. So what does it look like? What does it look like? That doesn't seem right, does it? Let's see. Okay, let me try that again. Maybe it's like. Yeah, I'm not really. There's like a unicursal aspect to this that I'm not doing a good job of drawing. Let me draw it with a picture, a version of it with just with dots, so I can sort of see the unicursal structure here. So what is it doing? It's like is this right? Now, what do I mean by unicursal? It goes there. Then it comes through here. Yeah, that can't be right. Let me try that again. It's supposed to be unicursal, but I'm apparently cheating. Let's see. So How can that be? Let's see. This is going here and here. Is there something unicursal that I'm trying to draw here? Let's see. This goes like this, like this, like this, like this, like this, and this.
Actually, this looks almost like a trefoil knot when you are done.
Really? Seriously?
Yep. I mean, if you put in over crossings and under crossings, or maybe, I mean a figure eight knot.
Well, that's a potentially interesting observation. So just goes to go up like that. And you're honestly telling me that that's a figure eight thing.
I'll look around for a picture of a figure eight knot, and I'll tell you if it's true.
Well, we don't have to particularly worry about it, but
you can go ahead. But now you got me curious.
Yeah. So
only the way a mathematician draws a figure eight, not the
right. So so how do I draw this? How do I put these edges in over here? So it's like that. Sorry, this is supposed to be black, 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 black. And then what? There's a thing like this, and a thing like this, and a thing like that, and a thing like that. Okay.
Let me just show you, just for fun. It
Yes.
is a figure eight knot.
Well, that's it.
Let me just take over for a minute.
Sure, go ahead.
Unfortunately, you can't see them both at once.
Right.
There it is. I think that's the same thing that you.
It does look like the same thing. I don't have any. I don't have any good story yet about why that should be happening. But we could try to invent stories. But I guess I'll think about that for homework.
Yeah, you can share your screen again.
Okay. So.
I mean, do you have any story about the unicursal nature?
I don't think so.
Yeah. Okay.
I don't think so. But you're hinting that there is some story of that.
Maybe. I mean, so if you can draw something unicursally and do alternating over and under crossings, then you're very much in the land of knots. But anyway, I don't know.
Yeah, okay, that's I got to think about that, but I'm trying to avoid thinking about it right now.
Yeah, sure, don't think about it.
So this picture that I've drawn over here is a picture of a design in Grothendieck's sense. And it's right, this is living on a genus zero thing. So it divides the Riemann sphere into 6 squares, so to speak. Is that right? Nah, yeah, I guess the outside region is a square. Yeah, and then there are 5 in the more inner part. So yeah, right. I mean, there are so many different conventions for how to draw designs. These squares are the so-called lozenges. Each square is actually 2 triangles. Right. What does each square have? It should have on the boundary. It should be a green and a red with 2 blues connecting them. So if you put in the edge, if you're in the extra edge from the green to the red, then you're dividing the square lozenge into the 2 triangles, which and the triangles are, you know, balanced in color, green, blue, and red. So what am I trying to say? That we're trying to find a Belyi map, Belyi projection. Yeah, we're trying to find, right. We're trying to find a rational function. Let's see. We're trying to find a rational function that gives one of these Belyi maps. So what am I trying to say? We're looking for a function, I guess I'll call it, for the moment I'll call it R of Z equals S plus the S sub 0 plus S sub 1 times Z plus, plus dot 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 up to plus S to the 6, S sub 6 of Z to the 6. That's the numerator, and the denominator I'll have T coefficients. So T0 plus T1 and plus T6. So I'm hoping this makes sense. I'm writing down a formula for a 6th degree rational function, which is the kind of thing that would, you know, give us, it would define, it would divide. I mean, what am I trying to say? It would, you know, there'd be the 6-fold branch cover of the Riemann sphere by itself. And that's what this picture is supposed to depict. So we're trying to, right, we're trying to look at the picture, and from the picture think of, you know, write down all the equations.
So this thing is supposed to take the value 0 at, is it at 6 different points?
It's supposed to take the value 0 at, okay, we have to set on a convention here just to keep things. I
don't know what the,
let's say green
convention is.
Blue and red. And yeah, there's some danger that right in the middle, I'll suddenly realize, oh, I want to switch my convention to something completely opposite. But I think I'll try, for now, I'll try infinity for the greens and 0 for the blues and 1 for the reds.
Greens are just C and D.
Greens are C and D, yes.
Okay. Green and blue look really similar on the screen. Maybe I'm going colorblind, but okay, I can still see. I can see it. Barely.
Yeah, no, I have a feeling it's not your color blindness. I have a feeling it's some other problem. But let's see.
Okay.
So yeah. Yeah, so right, okay. So I'm struggling to get this to make numerological sense. So what am I trying to say? That I'm trying to develop a system of equations here, which will, you know, the coefficients of R will be solutions of a certain system of equations, but we have, well, but we have some auxiliary variables here. So what am I trying to say? We're going to have, right, okay, so we're going to have some, degrees of freedom and some degrees of constraint. And, you know, degrees of freedom, we also call those variables. Degrees of constraint, we call them, I don't know, constraints. And so how many degrees of freedom we have here? Well, it looks like we have 7 degrees of freedom for the S coefficients. 7 degrees of freedom for the T coefficients, 2 degrees of freedom for the green dots, 4 degrees of freedom for the blue dots, and 2 degrees of freedom for the red dots. And then I'm trying to figure out how many degrees of constraint we have. And I'm thinking that for each dot, we are
Confused.
Yeah.
In the formula for R of Z, the only degrees of freedom are those 7 plus 7.
That's right. That's right. But then we're going to be evaluating R at these green and red and blue dots. And you know, the constraints, the equations that we're going to write down involve those, the locations of those red and green and blue dots. So those are auxiliary variables or something.
Okay, I guess. Yeah.
I think it'll make sense. I think it'll make sense. And the constraints that we're getting is that, you know, at any particular one of these green, red, or blue dots, you look at the number of edges coming out of it. And I think it's like that, you know, you can sort of think that each edge coming out of the dot is a constraint applying to that dot. Because what am I trying to say? Does that make sense? Let's see. Yeah, what am I trying to say? That
Well, like if you got like that blue, one of those blue dots with
yeah,
4 edges coming out of it. You're
yeah.
saying
So you're wrapping around twice. Yeah. So you're right. You've got something that's
double 0.
yeah, it's stationary to second order or something like that. So you're constraining the value, right? For a blue dot, we're constraining the value to be 0. But if it's got the 2 edges coming from it, then it's, you know, stationary to second order or something. So that's 2 constraints basically. So yeah. So what am I getting for the total number of constraints here? I think I'm getting, you know, for the greens, I think it would be 4 plus 2, I think. Yeah, it looks like C has 4 edges coming out of it. D has 2 edges coming out of it. For the blues, it would be E and F and G and H. It looks to me like 4 plus 4 plus 2 plus 2. And then for the reds, it looks like B and A is 4 plus 2 or something like that. So that seems okay. So this seems to be 22 degrees of freedom and 24 degrees of constraint. Does that mean I'm already in big trouble? Let's see. That numerology looks correct so far. I mean, those are pretty close. Is that close enough? Am I screwing up here? Let's see. So I mean, at one point I was thinking that the fact that we have, you know, the triple transitivity of the Möbius transformations on the Riemann sphere would like somehow, you know, save us with the, but is that going completely, is that completely the backwards direction? What am I trying to say here? So, right, what I'm sort of hoping for here, right? I want to get a 0-dimensional solution space.
Why do you want to? Except from the fact that that's nice.
Yeah, yeah. It's just the fact that it's nice. It's, you know, it's like combinatorial or something. I don't want any continuous parameters. But yes, this is.
Okay, so you don't really.
I don't have a good formal
theoretical
reason.
reason to think why you should get it.
Yeah, I don't understand why I'm entitled to that.
Yeah.
But it would be nice if we get it. And yeah, I was intending to do some like genus calculations here, or some calculations for genus 0 in general. What's the general numerological pattern here about the number of degrees of freedom and the number of degrees of constraint? What am I trying to say?
I'm completely not getting the right count or the same count of constraints. So could we go
Sure.
again?
Sure. I may have screwed up. If we can find places where I screwed up, then it might help.
Can I talk?
Go ahead. Yeah, go ahead.
So first I'll do zeros, and then I'll do poles, and then I'll do ones.
Okay.
So I'm getting 2 double zeros at E and F. I mean, I'm getting a double zero at E and a double zero at F. Is that a double zero, or are you saying it's a quadruple zero?
I'm thinking it's a quadruple zero, but I could be all screwed up.
Oh, why did I think it was a double? So you really think it's a 4-fold branch point? Okay, well, that would explain why I'm completely off.
Yeah, but I wish I could say better by why, you know, I think I fell into this same trap, but I'm not really sure which one is the trap and which one's the right way. But yeah, go ahead.
Well, I mean, that would mean all my things are off by a factor of 2. So
right.
So those black curves, that's like some of those black curves are the positive real axis, and some of those black curves are the
I think they're all the unit interval.
They're all the unit.
I think that's. Oh, sorry. No, okay. I didn't say that right. No, I didn't say that right. I didn't say that right. Oh, okay.
So some of them are the unit.
Okay, no, yeah, okay. Okay, I think you just found a big mistake I was making here. Okay. So let me, okay.
But are you? But
yeah. So
are
right,
you agreeing with me that those order 4 vertices, degree 4 vertices are double zeros instead of quadruple?
I think you're probably right.
It's like half of the edges are like going from 0 to 1, the other half are going from 1 to infinity or something like that. I don't even know if I believe that.
Well, you know what? Let me think.
Actually, I don't know if I believe that at all.
I think what you're telling me is that I really should put in the extra edge. Yeah, okay. I think I just completely screwed up. So maybe I should put in the extra edges here. The ones going from red to green. So there's these 6 missing edges here. Sorry, this is so disorganized. So there's one there, one there. So I just put in 4, and then there's another one here. And then there's this last one where I have to sort of break the symmetry. I'll put it over there. Okay, so now you're telling me that those edges is the whole real axis. That's where anything that's real value.
Positive real? No, the whole real axis. Yeah, yep. An edge going from a blue to a green is like the negative real axis. Yeah. Uh-huh.
Yeah. Boy, did I have this screwed up. But okay, I'm really hoping that it'll work out better this time. So, okay, so now you're telling me that, the sort of normal condition is that there's just one real axis for a point. That's an unbranched thing. Whereas, right, so we should divide by 2 always, you're saying. And right, we look at the number of edges at a point, we divide by 2, and that's the number of constraints at that point.
That's what I was thinking. That's why I was getting drastically lower number of constraints than.
And the fact that there were missing edges apparently. So okay, so let's try this and see if it works. So see if this works any better. So let me try this. We still have the 22 though, right? So
I'm happy with that.
So now what are we getting? So okay, now let me get to A, B, C, D, E, F, G, H. Okay, and it looks like you're telling me A has 2 constraints.
Can you stop moving it out of sight? Can you let the picture is going off my, now I just need to see the picture. Thanks. I need to see that.
Okay.
Enough for me to draw these millions of.
Sure. Yeah. This is so horribly disorganized.
It's not so bad, but I just, it takes, I'm not drawing it on the same.
Yeah.
I'm starting from scratch, and so there's lots of edges to draw here.
Yeah.
B to C. B to C, going twice. E to C, F to C, and then this one extra one. Okay, I think I have it. So you can go down. So you can still see it when you slide it out of my view. Is that true?
I don't know. Maybe I changed the size or something like that.
No. Anyway. Okay.
Now I'm wondering if I'm going to get the same bad numbers that I had before. Let's see. So I'm going through B. What do we have? We have. Right. It still looks like we're going to get 4 for B. So maybe it really is exactly the same, that there are 2s and 4s here. No, it's not right. No, that's not right. Okay. Okay. Right, because the blues have a different status than the reds and the greens, right? Okay, so okay, let's try this. So it looks like we have A is 2. Right, it's something like this, that for the greens, we have this Young diagram that's like 4 and 2. For the reds, we also have this Young diagram that's 4 and 2. But for the blues, I think we have this Young diagram that's 2 and 2 and 1 and 1, which is actually the transpose or something like that.
I don't remember how these Young diagrams are supposed to be shown up here.
Well, there's this, there's going to be this permutation with a 4 cycle and a 2 cycle for the greens, permutation with 4 cycle and a 2 cycle for the reds, and a permutation with a 2 cycle, a 2 cycle, a 1 cycle, and a 1 cycle for the blues.
I don't know why. Sorry, I don't know. Am I supposed to? Is that in the? I don't get that at all. Sorry.
So that's rotating. What am I trying to say? So,
I mean, if you just want to skip this, I don't feel an urgent need to understand this as long. I think we can do. I can do the counting. Oh.
Well, right. As long as we're doing it in such a disorganized way, there. Let's just go ahead and write down this numerology here. So it's going to be A and B is, I think, 2. Sorry, that's 2 and 4, I think.
Yeah.
Okay, and then C and D is going to be 4 and 2, I think. And then
Yeah.
and then E and F are 2 and 2, and G and H are 1 and 1.
E and F are 2 and 2. G and H are 1 and 1. 6, 12, 14, 16, 17, 18.
18?
Well, don't trust me. I'm really bad at that. Long lists of small numbers.
Okay.
Both do it, and we both get the same answer. Then, well, unfortunately, it's revealed mine. But
Sorry, I'm just doing a horrible job of maintaining the page here. What is this doing here? Have I now totally lost where the picture is? It's over there. Okay, this is equal to 18. Okay, so we have a gap of 4 here. Now you want to hear my silly story about why there's a gap of 4?
sure.
Okay, I think it's the triple transitivity of the, Möbius group. That's 3 of the 4. And the 4th one is just, the common factor between the numerator and the denominator.
So I definitely buy the common factor story,
Yes.
but if you're naming the okay, so yeah, so when you have, there's this 3-dimensional action of SL2
Yes, something like that. SL2C, yeah.
acting on things, and so that is acting both on the coefficients, those S's and T's, and it's also acting on the positions of the points.
Actually, the way I'm thinking of it, I'm only thinking of it as acting on the inputs, not acting on the outputs. Right, we don't want to think of it as acting on the outputs, right? Because in the outputs, infinity and 0 and 1 have very special, important conceptual rows. Those are the critical values. We don't let the Möbius transformations change the critical values. So we're having talking about the Möbius symmetry that just acts on the inputs, does not act on the outputs.
Okay, so you're trying to count these branch covers up to isomorphism, and the isomorphism, you're thinking of the base is locked in place. Yeah, I mean, the base is CP1, and numbers are what they are, and you don't get to change those, but the branch cover points on there are labeled in a somewhat arbitrary way, so you have to mod out by symmetries to count them up to isomorphism.
Right, that's what I think. And we can, perhaps gauge fix. I was imagining gauge fixing by having the first green, which is C, having that be. Yeah, right. I have the greens to be the poles. So I was going to have, yeah, at one point I was sort of trying to predict ahead of time where the poles were going to be. But I think that turned out to be a bad idea. But yeah, maybe gauge fixing is a bad idea, or at least at my stage of understanding, it's a bad idea. But yeah, but I was imagining doing it that at one time. But that probably got me confused with the dimension numerology. So yeah, so let's just think of it this way: that we've got right, and so I think I'm conjecturing, claiming, predicting that this slightly encouraging minor miracle should always happen. That whenever we have one of these genus 0 designs, and which means that we're trying to get a Bellier projection that's just a rational function, just a meromorphic function, just a rational function, that we'll always get this gap of 4 between the degrees of freedom and the degrees of constraint. And that gap of 4 will always be explained in this way. 3 for the.
So what's the theoretical / philosophical reason why this should be working? It's that you want to have like some.
Yeah, that's a great question. That's one of those slightly more conceptual questions that I'm probably not, because okay. Right. Let's think about what we're trying to do here. One thing that we're trying to do is we're really trying to test this example. This example came from the Jugendtraum, remember? And this, the Jugendtraum for me sort of predicts some examples of designs that should be in the same Grothendieck-Teichmuller orbit. I'm blaming this conjecture for predicting that, but I'm very uncertain about that conjecture. I really want to know, does this really work? Does this example that I predicted, or that the conjecture predicted to be in the same Grothendieck-Teichmuller orbit, are they really in the same Grothendieck-Teichmuller orbit? And that comes down to some very concrete questions here. We're trying to write down systems of equations, determine that we really have, the Bellier function for the Bellier projection for this design and the Bellier projection for this design. Those will actually be solutions of the same irreducible system of equations. That's what I'm really trying to test here. So that's a real concrete question. And because it seems to me like such an important concrete question, that gives me an excuse not to think about all these interesting abstract questions that you're now encouraging me to think about. So we should really come back to those interesting abstract questions at some point. But I just don't think I'm good at dealing with those abstract questions today. So what am I trying to say?
Okay, so anyway, yeah. I'm willing to forestall it, but you seem to have some kind of weird confidence that we'd get a discrete set of solutions to these equations that.
Yes.
Well, so of course it's sort of wonder, why did you know that I should correct you, completely correct your counts to get it to work out exactly right?
Well, I already thought, right? I already had some ridiculous story that was completely delusory, saying that my numbers made sense and they didn't, but now you've completely changed them, but they still make sense. I mean, there's just this kind of bravado about the fact that they should make sense, because if they don't, then we're dead anyway. So.
Okay. So, but there seems to, anyway, okay, we can put it off, but it seems to me that there's supposed to be something going on here. I just have to try to say it, even though I can't.
Okay, go ahead.
Something like, in the end, there's supposed to be some sort of purely discrete set of branched isomorphism classes of branched covers of CP1, and it's supposed to be discrete because it's supposed to be that this fairly discrete Galois group is acting on a profile thing, at least. Something
like that. There must be much better ways to say it when I really understand it. But yeah, that's. Yeah, okay. There definitely should be much better ways to understand this, but that's what I'm stuck with at the moment. It's just this kind of feeling that that we should deserve this.
Okay, cool.
So,
can you show me the picture? So you had two of the. Or what are you going to do? Are you going to work on this one? Or are you going to compare it to the other one?
Yes, we certainly are supposed to compare it to the other one. And now you got me wondering, if this one gave us this figure 8 knot, now you got me wondering what this other one gives. Right, the other one, I'm getting confused about what the other one looks like.
I'd like to see those pictures again, because I think last time at some point I gave up taking notes for these complicated pictures, and can you show me those pictures? And I just,
Yeah, I can, yeah. Again, I'm bad at switching back and forth here, but let me try to find something here. So
which picture were we just supposedly doing?
okay, you see my cursor here on this yellow thing?
Yeah, I saw that thing, and then I do have this picture where you like transformed it into this picture that looks like an atom, a cartoon atom.
Oh, yeah, right. Yes, is that?
Yeah.
Yes,
So
again, you have to remember that atom picture, that just looks like that's where you just have the green and red edges. Again, I get, the mistake that you just caught me in before was just me really stupidly getting confused between two of the different ways of thinking about designs. There's the lozenge picture, there's this other picture where you bisect the lozenges into triangles, so you have a triangulation. And there's this other picture where you only draw the bisecting lines, and that's so that's one of these things going on here. So so right here's the very rectangular one, and
yeah.
so there's one we get from the rectangular one, and and yeah, we could work it out.
Somehow I missed out on how you got from the atom picture,
yeah,
which just has the reds and the greens, to the picture you started in on today, which was this figure 8 knot. So that is supposed to be like the same thing, but you're including the blues as well.
Something like that. Yes.
So is this like because you're like always secretly working on this stuff with someone else, and that and that you came up with this figure 8? Well, it didn't start out looking so much like a figure 8 when you started drawing it, but so you worked out this other picture with the reds, greens, and blues at some point.
Yeah, but you can see it in the picture here, right? I mean, so you've got this, right? Can you see? I'm thinking visually at the moment. You see my cursor moving?
Yep.
Okay, and this is like a parallelogram or something like that. But we're going to double wrap this. We're going to, this genus 1 thing is going to wrap around this genus 0 thing. And right, so the new fundamental name would just be half of this. And that's this, yellow half here, right here. But the way we wrap that up is we're gonna, do like an origami tetra. I don't know what origami, how I act actually. But we're just gonna fold up this piece of paper, along this style. We're gonna fold it up, and you can right. There's a little purple triangle there. It's just the folding instructions for folding the yellow thing. And when we did that, we got this figure 8 thing. But how is that a figure 8? Well, the way it's a figure 8 is that what? Right, I have to say, is it the red, green, just the red, green edges, or is it all the edges? Let's see. I guess the figure 8 thing is just all the edges except the red, green edges, strangely enough. That's the lozenge boundaries, is the, so yeah, there are always, confusingly related alternative conventions for how to draw this combinatorial information. You can just draw the green, red edges, or you can just draw all the other edges except the green, red edges, or you can draw, the whole triangulation. There's a whole bunch of these, and you know, when you think about it, they're all very straightforwardly related to each other,
Yep.
but there's a maze of interconnections between them.
Okay, okay. Okay. Yeah, I don't really get it, but it's anyway, so so there's one of them. So then you're in theory, you could like do.
Yeah, well, so in particular, right. So one of the things that's bugging me on this screen that I've got right here, I don't see the figure 8 picture at all, really. The figure 8 picture isn't here. And that means when I want to figure out what the you know, evil cousin of the figure 8 picture is, that's not really on this screen either. But you really got me curious now about what it is. What is this other thing besides the figure 8 thing? Because you're
Right.
You know, maybe the figure 8 knot, maybe it's like co-ordinate to some other knot or something. I don't know. But
well, can you draw it? I mean, can you draw the thing?
can we draw the other one?
The design, yeah.
I guess we have 25 minutes left.
Well, I don't know if that's what
okay.
you want to do, but anyway, I'm wanting. I can't draw it. I'm too confused to.
Right. Let's see.
Carry it out.
Okay. Let me stare at this picture for a moment and see if I think I understand how to do it. I mean, I see this picture over here, which is, I think this is just the green-red edges. Yeah, it's confusing because, right, there's so many of these different variations. You know, there's the not, you know, the atom, the thing you're calling the atom picture, that's like a non-planar graph. We have, you know, disrespected the planar structure there. So let me think. Let me see. I'm trying to, okay, so I'm trying to stare at this picture here. Oh, wait a minute. Maybe it's this picture here, right to the left of it.
That's where you've discarded the blues, right?
Oh, discarded the blues. Okay, but that's not really what I want. Let me see. I don't want to discard the blues. I want to discard the green-red edges. Oh, but that's right. That's just a picture that looks like, right? That's just the 12 squares. Right, it's this picture without the diagonal edges, such as 12 squares. And then you hold that up. Ugh, I can't quite see it.
Well, we don't have to do this.
Yeah, we don't have to do it right now.
I do want to.
Let me go back and just write down as a homework assignment, another homework assignment. So where are we? So one of the, okay. So the homework assignment is, you know, mysteriously, this semi-mysteriously, this looks like a figure 8 knot. But what does the other one look like? So that's a little homework assignment.
Yep.
Yeah, which requires disentangling all these different drawing styles and stuff like that. But well, okay, right. I'm flailing around here. I've only got like 20 minutes left. But that's probably okay because I didn't, you know, I'm not about to suddenly, you know, write down a polynomial equation here. But that's what we're trying to do. We're trying to, you know, work out explicit, right? I mean, you just right? I sort of convinced us that we really are going to get 18 equations in 22 variables, and that 4 degrees of freedom left over. That's just the 4 degrees of freedom of this 2x2 matrix.
Yeah.
So it looks like it's going to work out. It looks like I have a lot of computational work to do getting this to work out. But and then I'm supposed to do it for this example, and I'm supposed to do it for the other example.
Right.
And I'm supposed to compare them and see that see if the prediction comes true, that they really give the same. If they are different solutions of the same irreducible set of equations. So they're the same under the action of the absolute Galois group. So that's the test that we're going to have. But okay, but now let me think a little bit conceptually about what this is supposed to mean. Okay.
Okay.
So what am I trying to say here? And I've probably mumbled something like this before, and I'm going to mumble it again right now. But what am I trying to say? That when we write down these equations, these are supposed to be speaking to us in some language, the language of, I don't know, I was going to say algebraic geometry. I'm not even sure that is the name for this, but something like, level of expressivity, some language, some doctrine, or something like that. And it's like we're saying as much as we can in that language. So we're constrained in what we're allowed to say. We can't just say anything we want. We have to speak according to the rules of the language. And so we can say things like, we should be able to say things like, this complex number is a solution of this equation that we can write down that tells us that we've got a 3 torsion point on the Gaussian elliptic curve or something like that, right? The idea of having a 3 torsion point, or the idea of having a primitive 3 torsion point on the Gaussian elliptic curve, that should be something that we should somehow be able to write down in polynomial equations, where the variables are, well, in this case, the variables should be just like the coordinates of this alleged primitive torsion point, primitive 3 torsion point, let's say. I hope that makes sense. So what does it mean to be a primitive 3 torsion point on the Gaussian elliptic curve? I hope that makes sense, and that it, because of the nature of the concept, that it translates directly into some polynomial equation or system of polynomial equations, but it's reduced to one polynomial equation. And that's where this conjecture that I have is coming from, right? So that we have these 2 Gaussian designs, and they should somehow, when you say as much as you can about each of them, it should be the same thing. You should find it impossible to distinguish between them in this language, even though we can easily look at the pictures and see that they're different. One has this rectangular fundamental domain, the other one has this skew fundamental domain. You and I can easily distinguish between them, but this restricted expressivity language of the polynomial equations, it just seems like it's going to, I'm hoping, I'm conjecturing that this is going to, illustrate how the Grothendieck model game works. That we're just going to, the most you're going to be able to say about what's going on here is that, oh, we have these torsion points on the Gaussian elliptic curve that's encoded in our polynomial equations, and that's it. There's nothing else you can say in that language, and that's my plan. I hope it works. It might be that it doesn't work at all, but that's my plan. To
I'm confused about where these what torsion points have to do with anything right now.
So okay, let me try to give a little spiel about that. So so we got Gaussian elliptic curve. And yeah, so there's sort of a duality between looking at torsion points and looking at unwrappings. I mean, it's just the duality between wrappings and unwrappings. So what am I trying to say? If you have the Gaussian elliptic curve, which perhaps I try to draw a fundamental square for it. Then, if we unwrap it, then we're getting, a larger fundamental domain.
Mhm.
Sorry, that's originally supposed to be 4 by 4, but somehow I do it 5 by 5, and then it all got screwed up. Let me start again. Yeah, if you start piecing these fundamentals together, you get some larger fundamental domain. That's it. But if you go the other way in, if so here the original one is like the codomain of this wrapping or covering map. Say it again.
So here you're modding out by the 2 torsion points in this picture.
Well, that's the way I kind of drew it, or something like that. But I mean, it's more like I'm unmodding out by it, right? In this picture, I started out with the smaller fundamental domain. I just placed others next to it, and I've got a larger fundamental domain.
Right.
It's like unwrapped.
Yeah.
But I equally well could have done it the other way around. I could have subdivided the original one.
Right.
And so because of that, I'm being sloppy here, but it should make sense that the torsion points on the original elliptic curves, studying those torsion points on the original elliptic curve by some sort of just duality between domain and codomain should be equivalent to studying these things that cover the Gaussian elliptic curve. Right, because what am I trying to say? The
cover it, or that it covers?
Well, that's the trick. You just have to work it out, whichever way it is. So the point is that, right, because both, right, you're covering the one Gaussian elliptic curve by another one. So you can just play all sorts of games.
Okay.
So, so what I'm saying is when you have the Gaussian elliptic curve covered by itself, and perhaps by, but this covering map could be multiplication by a particular Gaussian integer.
Mm-hmm.
And so when you're doing that, am I saying this right? I want to say that the kernel of the wrapping map, the kernel of the covering map, is the torsion points. And just there's this interplay between the domain and codomain.
Okay.
So it's kind of like that. So that when you're, I'm saying very sloppy, but when you work out the Belyi coefficients of the Belyi projection, the rational Belyi, the meromorphic rational Belyi projection, the coefficients as a rational function, when you work out the polynomial equations governing those coefficients, it should be the same as working out the polynomial equations that govern the coordinates of the torsion points.
Okay.
Modulo a few, algebraic games, a few glitches here and there. Those two projects should be, pretty much equivalent. Or at least enough to motivate this conjecture that the Kronecker's Jugendtraum, specialized to the Gaussian case, will give us a way into the Grothendieck-Teichmuller theory. And so So that's
Okay.
the idea. I mean, so that's the idea. So we have this, right, we have this very concrete project to try to explicitly, concretely work out these polynomial equations and see if we really are getting, you know, these two different examples, that they're really solutions of the same irreducible system of equations. That's the one very concrete project. But it's, you know, one of the important conceptual interpretations of that concrete project is, you know, trying to understand how allegedly the reason why that they should work out to be solutions of the same irreducible set of equations is because the most that you can say about either of them applies to the other one in this language with restricted expressivity. According to the conjecture, the most that we can say about this one design is just as equally applicable to this other design, because they're both conjecturally just defined in terms of these torsion points on the Gaussian elliptic curve. So is there anything we should do before we quit here? Maybe not. I mean, like I say, the rest of, you know, it seems like the next thing that needs to be done is, you know, just more concrete work here to really try to work out these systems of equations and test whether they really work. And that sounds like probably homework work. I was going to spend I was going to spend a certain amount of time just trying to work out the numerology of the number of constraints versus number of degrees of constraint versus number of degrees of freedom, because I was really confused about that. But I think you cleared through that. I think you just, you know, pushed me in the direction. I mean, we didn't check very carefully whether this is going to work, but I think this works because previously we had a, you know, just kind of numerological rule that made sense when we were dealing with the case where the Bellier projection was just a polynomial function. So like that was the case where there was just one blue dot, you know, lots of green dots, lots of red dots, just one blue dot. And it was all genus 0. And I think that's the case where it works out to be a tree, and it works out to be, you're just dealing with a polynomial because there's just one pole, right? When you just have one pole, then I think you can just think of it as a polynomial or something like that, and everything works out. And so I think we worked out the numerology in that case. I think I, you know, worked it out in a very ad hoc way. And you know, a lot of it had to do with just staring at Euler's Euler characteristic formula, the vertexes plus, what is it? Vertexes plus faces, vertexes minus edges plus faces or something. It's the Euler characteristic. So, I mean, that gives you the genus. Somehow the Euler characteristic translates into the genus of the surface and everything like that. And well, right. So, right. Again, there's this minor miracle that we're hoping for, that that the system of equations will be perfectly balanced between freedom and constraint, so that the solution space will morally just be this discrete thing, which will be, you know, in the land of absolute Galois. So yeah, previously I had, you know, in a sloppy ad hoc way, I had worked out that polynomial case. But now it looks like, you know, now it looks like when you fixed this thing, now it looks like it's working for the rational functions, not just for the polynomials. I mean, I have to go home, right? Part of my homework is to go home and check that when you specialize this way of handling the rational functions that I'm claiming you've now told me here, I just have to check that that specializes to the same allegedly correct way of handling the polynomials, right? Because the polynomial case should be a special case of the rational. So that's another one of my homeworks to check. But again, that seems best handled as homework. So I'm not sure I have anything else to say right now. Do you have anything else to say right now? I'm actually happy with how much progress we made today. I mean, even though it was totally disorganized based on
No,
lack
that's
of
fine.
sleep. Yeah, go
Yeah,
ahead.
yeah. No, I don't have anything much more to say. I think it's fine to quit while we're at
Yes,
it.
yes, yes.
I-
And I'm also hinting that you know, that when I'm not so short on sleep, that there's some really interesting, you know, higher brow stuff going on here. I mean, we really want to relate this to motives in the language program. I can't say anything in terms about that right now because I'm just not awake enough. But is there anything I remember about that I was going to say about that? I'm trying to threaten or promise to say something about that when I'm more awake. But all right. So thanks a lot, and
Yep.
yeah, there's a possibility I might have to cancel next week, but we'll sometime very soon we'll meet again.
Oh, by the way, we're about to
Yeah.
come to this discontinuity which is around Halloween, where
Yeah.
the daylight savings time kicks in one of our two countries here, but not yet the other.
I wonder if that's going to help or hurt in terms of my trying to adjust.
Well,
Yeah.
I'm so confused. Yeah, I don't even remember like which country does daylight savings time.
Well, it
first.
doesn't matter as long as you know something else.
Well,
yes.
yeah. Well, anyway, but it's like a 1 week worth of
Yes.
things being different. So it's
So you really think it is true that one of them I mean, I heard Mexico just abandoned daylight savings time, except along the border, because you know all the sensible countries are now abandoning daylight savings time. So that makes it sound like UK is abandoning it or something.
No, I didn't say it's abandoning it. I said it starts at a different day in the US. So for the UK, it's daylight saving time ends on the 30th of October, which is this Sunday.
Okay.
And then I'm just looking this up. And then for you in the US,
yeah,
it ends on Sunday, November 6th. So next Monday, sorry, next Friday, 1 week from now, I will have ended daylight savings time. So I will have shifted relative to you.
Okay, but so
we can worry about which way later.
right. So there's a real good chance I'll just miss the week, and that will make it easy to do the calculations because it just won't happen. That would make it
that's great. That's great.
But I can't promise that yet. The alternative would be that we
promise to miss the meeting.
The alternative would be that we would just follow your schedule, whatever your clock, whatever your personal or social clock says.
Well, it may be that because I'm also talking to Joe and Todd, who are in the United States, on the same day.
Okay.
That's possible that I should knuckle under and.
Yeah. Okay. Okay.
Anyway,
we'll have to work
I'll
that
let you know. I'll let you know.
Okay.
Yeah.
Okay. Yeah. Right. We'll both have to let each other know because I'm not sure what's going on yet. Okay.
Yeah.
So okay. So thanks a lot and bye for now.
Yep. Okay.
Okay.